Morty's rotational Rick, back talking to you about volumes of solids with known cross-sections. I got another question. What do the nuclear physicists always get for lunch? Fish and chips! I'm trying to read!
First thing we're going to do is review the area of a region bounded by two curves. So recall, if you want to find the area between two curves on a given closed interval from A to B, all you have to do is evaluate the definite integral from A to B of your upper function on that interval, which in this case would be f of x, minus your lower function on that interval, which in this case would be g of x. If you evaluate that definite integral, it'll give you the exact area between these two functions or these two curves on that given closed interval from A to B. First vocabulary term is a cross-section. That would be a surface or shape that is or would be exposed by making a straight cut through something, especially at right angles to an axis. So in our examples down here, we have a square prism and we have a cylinder. And as you can see, if we want to find the horizontal cross-sections for each of these three-dimensional figures, all you're doing is you're taking a slice through that given prism and looking at what shape it is. So if I were to slice this prism horizontally, I see that the shape that's created in here, this cross-section, would be a square. If I slice this cylinder horizontally, I see the shape in here that would be created would be this circle. So a square would be the horizontal cross-section of a square prism. A circle would be the horizontal cross-section of a cylinder. It's important to be able to recognize what shapes these cross-sections are, because today what's actually going to happen is you're going to integrate the area formulas for certain cross-sections and you'll end up finding the volume of certain three-dimensional figures, and we'll show you that in a second. Next, let's talk about volumes using cross-sections. So this says to find the volume of a solid with a known cross-section, like a square, triangle, etc., take the definite integral of the area of the given cross-section over the specified interval. So let's say we have a three-dimensional figure like this, and we want to find the volume of this figure. What we're going to do is we're going to integrate from x is equal to 0 to x is equal to whatever x value this is. The area formula for one of these cross-sections, which in this case would be a rectangle. If I were to integrate the area formula for a rectangle on this given interval from this x value, x is equal to 0, to this x value, whatever that may be, it will give me the exact volume of this three-dimensional solid that has rectangular cross-sections. Now note, this is very similar to the way we find the exact area under the curve. When we integrate to find the area under the curve, we're technically adding up the areas of an infinite amount of rectangles. Here, we're technically adding together the volumes of an infinite amount of rectangular prisms with width of dx, or delta x. So again, all you need to note is that in order to find the volume of a three-dimensional figure with known cross-sections, you know what shape the cross-section is. You can just integrate the area formula for that cross-section on your specified interval. That will give you the volume. Now let's talk about the areas of common cross-sections. So some of these you know, some of these you don't. If I want to find the area of an equilateral triangle, what I'm going to do is I'm going to take one of the sides, because they're all the same. I take one of the sides, I square that, and then multiply it by rad 3 over 4. That'll give me the area of an equilateral triangle. Area of an isosceles right triangle, since both of the legs are congruent, I just take 1/2 base times height, or in this case, 1/2 b times b, or b squared. Here, the area of a square we know is just the length of one of the sides squared. The area of a circle formula we know is pi r squared, and the area of a semicircle, remember a semicircle is just half of a circle, so the area of a semicircle formula is just 1/2 times the area of a circle formula. Now the reason we're reviewing these is because today these may be the cross sections of your three-dimensional figure, and if one of these shapes represents the cross sections of your three-dimensional figure, what you're going to do is you're going to integrate the area formula for one of these cross sections on your given interval. When you do that, that'll give you the volume of your three-dimensional figure with these known cross sections.
You heard any good jokes about sodium? Nah. It's example time.
Now example 1 says the base of a solid is the region bounded by the given lines. The cross sections perpendicular to the x-axis are squares. Find the volume. So the goal of this problem is to determine the volume of this three-dimensional figure right here. So how was this three-dimensional figure created? Well, to determine that, we have to look at this little blue triangle over here. This blue triangle is the region bounded by the lines. X is equal to 0, f of x is equal to 1 minus x over 2, and g of x is equal to -1 plus x over 2. Now what happens is in this this figure right here, we're going to create little tiny square prisms that are perpendicular to the x-axis that pop up from that blue region on the x and the y-axes. These square prisms are going to have the same base as they do height. So this distance between f of x and g of x is going to be both the base and the height of each of these square prisms, whereas the width is going to be dx, or delta x. Now, if you were to create an infinite amount of square prisms from x is equal to 0 to x is equal to 2, you get this three-dimensional figure that looks like this. So our goal now is to find the volume of this three-dimensional figure. So how do we do that? Well, we need to set up a definite integral on this given interval of the area of this cross-section formula. So in order to write that definite integral, our first step is figuring out what is our interval. So the interval, remember, if you looked at the graph, we were going from x is equal to 0 to x is equal to 2. But if you forgot that, remember, you can always set these two functions equal to one another and solve for x and figure out where these two functions intersect. So we're going to set f of x equal to g of x and solve for x. So how do we solve this for x? Well, we multiply everything by 2 to get rid of the fractions. We then add 1 to both sides. We get x is equal to 2. So these two functions equal one another at x is equal to 2. But that's only one x value. What would be the other x value of our interval? Well, it says we're starting at x is equal to 0. That's one of the lines that's bounding our region. So we know our interval is going to go from x is equal to 0 to x is equal to 2. The next step is to figure out what is the area formula for our given cross-section. Remember, in this problem, the cross-sections are squares that are perpendicular to the x-axis. What's the area formula for a square? That would be the length of one of the sides squared. So the next thing we have to determine is the length of one of the sides of our square. How do we do that? Well, remember, the length of one of the sides of our square is going to be the distance between our two given functions here, because our squares are perpendicular to the x-axis, meaning that the length of the base of the square is going to go from one of the functions to the other function. So the question is, which function is the greater function on this given interval? Because if we know that, then we can take the upper function and subtract the lower function to get the distance between those two functions. So let's determine which function is greater on this specific interval. What we're going to do is we're going to pick an x value on this given interval and plug it into each of these functions for x and see which produces a greater y value. So I'm going to take 1, plug it in for x in each of these functions, and it looks like on this interval, f of x produces greater y values than g of x. Therefore, f of x is going to be greater than or equal to g of x on this given interval. So all I have to do now is set up my definite integral on this given interval of the area formula for my cross-section. And remember, in this problem, the cross-sections are squares that are perpendicular to the x-axis. So I'm going to set up my integral from x is equal to 0 to x is equal to 2 of the area formula for a square. What's the area formula for a square? The length of one of the sides squared. So what would be the length of one of the sides of this square? Well, again, we said the length of one of the sides is the distance between f of x and g of x, our upper function and our lower function. So to find that, you would just take f of x and subtract g of x, and that will give you the distance between these two functions. Now, if that's the length of one of the sides, then the area formula for this square here, one of our cross sections, would be f of x minus g of x, the quantity, squared. This will give you the exact volume of that solid that we saw at the beginning. So now all I have to do is evaluate this definite integral. I'm going to plug in what each of those functions were equal to, and now I simplify inside of the brackets. 2 minus x, the quantity squared, is the same thing as 2 minus x times 2 minus x, so I FOIL that out, simplify, and now I can evaluate this definite integral using the fundamental theorem of calculus. So the first step would be to take the antiderivative of each of these terms in here separately. When I do that, I can then use the fundamental theorem of calculus. I take the upper limit of integration 2, plug that in for each of the x's, and subtract. When I take 0, my lower limit of integration, and plug that in for each of the x's. I then simplify these, and I end up getting that the volume of that three-dimensional solid, whose base is the region bounded by these given lines, and whose cross-sections are squares that are perpendicular to the x-axis, is 8/3. So again, what this is doing is it's adding up an infinite amount of volumes of square prisms on this given interval from x is equal to 0 to x is equal to 2, where this is the base times the height, and this is the width of each of those prisms. Now, because we're taking the integral, the width of each rectangular prism, that dx, is approaching 0, thereby creating an infinite amount of these square prisms that make up this three-dimensional solid. And the integral here is just adding up the volumes of the infinite amount of square prisms that we have created to fill this three-dimensional figure. That's why this is giving us the exact volume of this three-dimensional solid. Now, example 2 says the base of a solid is the region bounded by the given lines. The cross sections perpendicular to the x-axis are equilateral triangles. Find the volume. So I want you to notice this time we're dealing with the exact same lines, the exact same region. We have the region bounded by x is equal to 0, the function f of x is equal to 1 minus x over 2, and the function g of x is equal to negative 1 plus x over 2. It creates this blue triangular region right here. The only difference this time is that the cross sections of this three-dimensional solid that are created are equilateral triangles that are perpendicular to the x-axis. So instead of being squares that are popping up from our axes, it's actually going to be equilateral triangles, creating this three-dimensional figure right here. So the process in finding the volume of this three-dimensional figure is exactly the same. We're going to integrate on our given interval the area formula for one of the cross sections here, and that cross section this time is an equilateral triangle. So in order to write that definite integral, our first step is figuring out what is our interval. So the interval, remember, if you looked at the graph, we were going from x is equal to 0 to x is equal to 2. But if you forgot that, remember, you can always set these two functions equal to one another and solve for x and figure out where these two functions intersect. When you do that here, you multiply both sides by 2, you simplify, you end up getting x is equal to 2, meaning these two functions intersect at x is equal to 2. The region that we are integrating on is also bounded by the line x is equal to 0, meaning that our interval on which we're going to integrate is going to go from x is equal to 0 to x is equal to 2. So we have our interval. The next step is to figure out what is the area formula for our given cross section. Well, it's an equilateral triangle. And we saw that the area formula for an equilateral triangle is rad 3 over 4 times one of the sides squared. So all we have to do is figure out what is the length of one of the sides of our equilateral triangle. Well, because these equilateral triangles are perpendicular to the x-axis, that means to find the length of one of the sides of the equilateral triangle, all we have to do is just take our upper function and subtract our lower function. That'll give us the length of one of the sides. So how do we determine which is our upper function, which is our lower function? We're going to choose some x value on this given interval to plug into both of these functions. When we do that, we see which produces a greater y value. Whichever one that is going to be the greater function on this given interval. So what's an x value on this interval that I can plug in? How about 1? I'm going to plug in 1 to each of these functions for x and simplify, and I see that f of x produces greater y values on this given interval than does g of x. Therefore, f of x is going to be greater than or equal to g of x on this given interval. Now that I know that, I can create my definite integral. It's going to be the integral from a to b of the area formula for my given cross section, which in this case is an equilateral triangle. So what is the area formula for an equilateral triangle? We said it's rad 3 over 4 times the length of one of the sides squared. Well, we just said to determine the length of one of the sides of our triangle, it's just going to be the distance between f of x and g of x, or f of x minus g of x. That will give you the base of one of your equilateral triangles. So we square that side length, so it'd be the quantity f of x minus g of x squared times rad 3 over 4. That'll be the area of this equilateral triangle cross section. Now all I have to do is evaluate this definite integral in order to get the volume of this three-dimensional figure. So how do I evaluate this? Well, I'm going to start by plugging in what each function is equal to. I can then take this rad 3 over 4 because it's just a constant. I can move that out front of the integral sign, multiply it on at the end. I can simplify inside of these brackets here, and then 2 minus x, the quantity squared, is the same thing as 2 minus x times 2 minus x. So I FOIL that out and simplify, and now I'm ready to evaluate this definite integral. So in order to evaluate this, what I'm going to do is take the antiderivative of each term separately. I then use the fundamental theorem of calculus. I take my upper limit of integration, plug it in for each of the x's, and subtract when I plug in my lower limit of integration for each of the x's. When I simplify this and multiply that rad 3 over 4 on at the end, I end up getting that the volume of the three-dimensional solid whose base is the region bounded by these lines and whose cross sections are equilateral triangles is 2 rad 3 over 3. Again, looking at our graph, what we just found is the volume of this three-dimensional solid, whose base is bounded by these three lines and whose cross-sections are equilateral triangles. Again, what this represents is the sum of the volumes of an infinite amount of triangular prisms that go from x is equal to 0 to x is equal to 2. If you add up the volumes of an infinite amount of those triangular prisms from x is equal to 0 to x is equal to 2, it gives you the exact volume of this three-dimensional figure here. Now example 3 says the base of a solid formed by cross-sections is the region bounded by a circle of radius 2 centered at the origin. The cross-sections perpendicular to the x-axis are equilateral triangles. Find the volume. So because we're not given anything here, it'd probably be smart to make a sketch. So we have a region bounded by a circle of radius 2 centered at the origin. So we're going to create a circle whose radius is 2 centered at the origin. Now the question is, do you know the equation of a circle? Yes, the equation of this circle in particular is x squared plus y squared is equal to 4. Now, if I were to solve that for y, what happens is I get two separate equations, two separate functions, where I have y is equal to the square root of 4 minus x squared, and y is equal to the negative square root of 4 minus x squared. That creates your semicircle on top and your semicircle on bottom, respectively. So what's happening here is we have this circle, and in this circle, we are having equilateral triangles that are perpendicular to the x-axis pop up from this circle to create a three-dimensional solid like the one that you see here. So we need to find the volume of this three-dimensional solid. In order to do that, we need to set up a definite integral from x is equal to negative 2 to x is equal to positive 2 of the area formula for our given cross-section of this three-dimensional figure. So the first thing we need to do in setting up that definite integral is determine what is our interval. What interval are we going to integrate on? Well, we just saw in our graph, we are integrating from x is equal to negative 2 to x is equal to positive 2 because we have a three-dimensional solid whose base is a circle of radius 2 centered at the origin. So we're going from x is equal to negative 2 to x is equal to positive 2. The next thing we need to figure out is what is the area formula for our given cross-section? Well, remember, we have equilateral triangles that are perpendicular to the x-axis that are popping up from the circle. So what is the area formula for an equilateral triangle? That's rad 3 over 4 times one of the sides squared. So remember, the length of one of the sides is going to be the distance from the top of your circle to the bottom of your circle, meaning it's going to be the distance between f of x and g of x. So we have to determine which is the upper function on this interval and which is the lower function. Well, we already know. We saw f of x, where it's the positive square root of 4 minus x squared, is above g of x, which is the negative square root of 4 minus x squared. So f of x is going to be greater than or equal to g of x on this given interval. Now all we have to do is set up our definite integral from a to b of the area of our given cross-section. Now we know our a value is going to be negative 2, our b value is going to be positive 2. The area of our cross-section, we know those are equilateral triangles that have area formulas of rad 3 over 4 times the length of one of the sides squared. And we know the length of one of the sides of your equilateral triangle, because it's perpendicular to the x-axis, it's just the distance between f of x and g of x, or f of x minus g of x. That will give you this distance right here, which will be the length of one of the sides of your equilateral triangles. So when we plug all that in, it's going to look like this. We have the integral from negative 2 to 2 of rad 3 over 4 times the quantity f of x minus g of x, one of the sides of our equilateral triangles, squared. Now all we have to do is evaluate this definite integral to find the volume of that three-dimensional figure. So the first thing we're going to do is we're going to plug in what each of those functions are equal to here and simplify inside of our brackets. So if we were to simplify in here, rad 4 minus x squared minus negative rad 4 minus x squared is the same thing as plus positive rad 4 minus x squared, so it becomes 2 rad 4 minus x squared. Now if we are squaring this, what's going to happen is we're going to square the 2 and we're going to square the rad 4 minus x squared. So we end up getting 4 times the quantity 4 minus x squared in here. Now the cool thing is that this 4 right here is just a constant that I can move out front of the integral and multiply to the rad 3 over 4. And the 4's actually cancel each other out, just giving us rad 3 in front of our integral. Now all we have to do is evaluate this definite integral. So we're going to take the antiderivative of each of these terms in here. We then use the fundamental theorem of calculus to evaluate our definite integral. We take our upper limit of integration 2, plug it in for each of the x's, then subtract when we plug in our lower limit of integration, negative 2 for each of the x's. We then simplify in each of these parentheses, and once we do and multiply that rad 3 on at the end, we end up getting 32 rad 3 over 3, which is the volume of the three-dimensional solid whose base is a circle of radius 2 centered at the origin, whose cross-sections are equilateral triangles that are perpendicular to the x-axis. So now we can confirm that we did this correctly with our 3D rendering here. It looks like that one of the side lengths of our given equilateral triangles is just the distance between rad 4 minus x squared and negative rad 4 minus x squared. So it looks like we set this up properly. And in order to find the exact volume of this solid that's being generated, what you're going to do is you're just going to add together the volumes of an infinite amount of triangular prisms along this interval from x is equal to negative 2 to x is equal to 2. That's what this definite integral had you do. Now example 4 says the base of a solid formed by cross-sections is the region bounded by the graphs of the given equations. The cross-sections perpendicular to the x-axis are semicircles. Find the volume. So we again are given a three-dimensional figure, and the base of this three-dimensional figure is bounded by the graphs of these equations. F of x is equal to rad x is equal to 0, x is equal to 9, and y is equal to 0. Now in order to find the volume of this three-dimensional figure, because we know what the cross-sections are, we know that they are semicircles, we can just set up a definite integral from, in this case, x is equal to 0 to x is equal to 9 of the area of one of these semicircles. So let's go ahead and do that. In order to set up one of these definite integrals, the first thing we need to find is the interval on which we're going to integrate on. What we just said, it's from x is equal to 0 to x is equal to 9. They give it to us in the problem. Next, we need to determine what is the area formula for our given cross-section. So our cross-sections are semicircles that are perpendicular to the x-axis. So the area formula for a semicircle is 1/2 pi r squared. So all we need to figure out is what is the radius of one of these semicircles. Now if you recall from our figure before, our semicircle starts at the x-axis and goes up to the function f of x is equal to rad x, meaning on our given interval, f of x is clearly going to be above the x-axis. So f of x is going to be greater than or equal to g of x. So how does this help us? Well, it's going to help us in determining the radius of our semicircle. So let me show you how this works. In order to find the volume of this three-dimensional solid that we're creating, it's going to be the integral from a to b of the area formula for our given cross-section. And remember, we know what a and b are now. It's from 0 to 9. And the area of our cross-section formula, that's 1/2 pi r squared. That's the area of a semicircle formula. Now, our semicircle is going from f of x is equal to rad x to g of x is equal to 0, meaning the diameter of this semicircle is f of x minus g of x. But we don't want the diameter. We want the radius. The radius is just going to be half of the diameter. So the radius of this semicircle is going to be 1/2 times f of x minus g of x. So if we plug that into the area of a semicircle formula, it's going to look like this: 1/2 pi r squared, where r is the radius of this semicircle, 1/2 the distance from f of x to g of x. So all we have to do now is plug in what we know these functions to be, simplify them, and evaluate that definite integral. So I'm going to plug in what I know each of these functions are. F of x is rad x, g of x is just 0. If we simplify inside of these brackets and then square, we end up getting x over 4. Now, this is technically 1/4 times x. That 1/4 I can bring out front, multiply it to the pi over 4 that's already out here, and now I have pi over 8 out front of my definite integral. Now all I have to do is just evaluate this definite integral, multiply my answer by pi over 8. That'll give me the volume of our given solid. So how do I evaluate this? Well, I need to first take the antiderivative of our function here, which is just x squared over 2. I then use the fundamental theorem of calculus to evaluate here. I take my upper limit of integration, 9, plug it in for x, and subtract when I take my lower limit of integration, 0, and plug it in for x. I subtract each of those, simplify, multiply by pi over 8, and I get 81 pi over 16, which is the volume of the solid, whose base is the region bounded by these lines, and whose cross-sections perpendicular to the x-axis are semicircles. So we can again check out the 3D rendering of this to make sure we did it right. Remember, the radius of the semicircle was the only thing we needed to find, and that was just half the distance from our function f of x up here to our function g of x down here, or rad x and 0. If you subtract those two, divide it by 2, that'll give you the radius of our given cross-section semicircles. And don't forget, the integral gets you the exact volume of this particular 3D solid right here.